I guess the title was Computer Science or something like that, or Computers and Homotopy Theory. So I'm not entirely sure what part of my work I will be speaking about, because I would also appreciate having questions being asked during the conversational part of, during the talk. So I'll try to explain, and thank you, Barney. I'll try to explain a little bit what I'm working on right now. So so here is the story. So there is an area in theoretical computer science which is called type theory. So let me try to explain what it is about. It developed as in a sense as an alternative to classical logic. As an alternative to classical logic, which is more convenient. It's actually some kind of a combination of logic and set theory in a sense. So it's something which can be used by computer scientists to describe what computer programs should do. So I will. It's probably standard to consider it as a kind of alternative to logic or to set theory. So in logic, we have the units of expression are so in logic and in type theory. So the units of expression in logic are sentences. So a typical logical sentence would look something like that. For all x, let's say in the language of set theory, for all x, I don't know what is the syntax to. Maybe I should put a point here. It's not true that x is a member of x. That would be a sentence of set theory. So set theory is a theory where one can use the standard logical operations, which would be for all exist, no, and, or, and let's see what else we have. We have also imply, which we can express through the others. So this is common to any. This is common to any what's called first order language in classical logic. There are rules of deduction, and but in order for this to start working, one also needs to have some kind of elementary properties of entities. So in set theory, there is only one expression which can be used to build formulas and sentences, and this expression is x belongs to y. So the classical set theory has only one, as it's called, propositional symbol or predicate, which is something belongs to something, and then all the standard ways of operating with this expression. So this is a logical statement, and then I can make something like for all x, for all y, for all z. Probably should put some kind of dots here. X belongs to y, implies y belongs to place there exists T in Z such that, I don't know, Y belongs to T. That would be a slightly more complicated statement, quite typical one in Zermelo-Fraenkel theory. So we were all taught that Zermelo-Fraenkel theory is somehow a theory of sets. It's in fact not true. I mean, it can pretend to be a theory of sets. It can also pretend to be a theory of which can be used to create listings of products in a supermarket. It can be used almost for anything. But what it actually is, it describes so-called sets are in fact trees. They're trees with certain properties, because as we know, the way in Zermelo-Fraenkel one approaches things is one starts with the empty set. Then there is an axiom which says that for all x there exists a unique. Oh yeah, I forgot. I should have said it. There is also equality, which is very important. So there is equality and this sign for belongs. So there is an axiom which says that for each x there exists a unique y such that for all z in y, z equals x. So that's the axiom which says that for each x there exists a unique new set y which has only one element, namely x itself, and it's typically denoted by this. So starting from there being an empty set, which is an axiom which says that for all x, which is an axiom which says that there exists a unique, the fact that it's unique can be proved, but x such that for all y, it's true that y is not a member of x, and that's the definition of the empty set. And so if you have an empty set and then you have this, then you can form this and this and so on. One can also do other things, but the point of the matter is that everything is being built out of empty set. And in fact, if I have a set in Zermelo-Fraenkel theory, so it has a bunch of elements, but each element is a set by definition, because there's nothing else but sets in that. So, so this, one can draw it like this. So this is my main set, which I'm trying to describe. It consists of elements, but each element is a set. So it consists of elements. Probably there are no elements here, for example. And then each element is again a set. So it consists of elements and so on. So in fact, every object described in Zermelo-Fraenkel theory is naturally a tree. And there are precisely two conditions which describe all the trees which can be obtained in this way. And the first condition is that, so as an axiom of set theory, it's the axiom that two sets are equal if and only if they have the same elements. So it means that two sets must be distinguishable from the tree structure of their elements. So what it means that each tree has a property that it's a rooted tree, and it has a property that all the branches are different, non-isomorphic. So all branches at the vertex are distinct, non-isomorphic. And the second property is that everything has to be built up in a finite number of steps from the empty set. And that relates to the fact that if I take any of the, what are they called? Any of the leaves of the tree, then there is a finite, the number of steps to go from the leaf to the root is finite. So for each leaf, the depth of it is finite. That doesn't mean that it's bounded uniformly. For example, one can have a natural numbers are represented by a tree which looks like this. And so, wait, no. Well, that's one way of doing it, but we can do it another way also. No, this is not a way to do it, because this would be not permitted according to the first rule. Because we would have a tree where all these three branches are the same. So that is not allowed. So instead, what one does to represent natural numbers is this, then this, then this, this, and so on. So again, each leaf has only finite depths, but the depths are increasing, so we have infinitely many non-isomorphic graphs sticking out of one point. Now one can do obvious things with this. For example, one can consider all subsets in here, all subgraphs. All of the subgraphs will be different, and there will be uncountably many of them. So this way, one can represent an uncountable set. Now that's a bit of a strange way my explanation is taking me, but I think it's very important to understand. So now, how does one encode something like a group in set theory? So one starts with doing the following. One says, let's define what is a pair. This is a definition. X is a pair. And now let me try to invent it, because I don't exactly remember it. So the idea would be if I have two sets, x and y, and I want to form a pair out of them, then I form a new set, which consists of let's see what I should do. I think I should take the first, just in case. How about it doesn't work very well if x equals y.
And you simply take x and the set consisting of only y. And so
if I take x, but I still can get into trouble if x is the set which consists of only y. Because I do need.
this is how I was taught,
Is
Is it supposed to be an ordered pair?
No, it's not ordered, but the idea is that you have maybe
what you wrote was fine. You can recover.
x and then.
And then the second thing, x and y.
But this x and y is going to degenerate into x if x equals y. So in the case when x equals y, this will be x comma x in and x cannot be equal to x because of this. A set cannot be an element of itself. So okay, so this is called a pair. So let's see what it means actually for something to be a pair. For something to be a pair, it means that.
Axiom for these trees that the whole tree can't be a branch or something. The set that can't be a number of itself.
I don't entirely remember the whole axiomatics. It might be an axiom or it might be a theorem. So I don't really remember. So let's see what is a pair then. So a pair is a set Z such that there exists A in Z, there exists B in Z, such that for all C in Z, C equals A or C equals B. That would be a definition of element of set with two elements. And there exists, how about a pair of X and Y? Then it will be easier a little bit. So if there exists B in Z such that for all C in Z, C equals X or C equals B, and and for all D in B, D equals X or D equals Y. I think that would be a definition of a pair if you really wanted to write it down as a formal statement. Now, you can ask what is a group. So we know what is a group. A group is a set together with a map and a bunch of other things. So to encode it all in set theory, what one needs to do is to represent it as a kind of embedded pairs. So it will be a set. And then so a map between sets is also a set. So so a map from X to Y. What is a map from X to Y? It's probably a triple which consists of a set X. So we don't have a triple, so we'll need to work with pairs. So it will be a pair which consists of set X together with a pair which consists of set Y and set Z, where set Z is a subset in the product of X and Y, something like that. Now, I'm not trying to make fun of you. I mean, that is precisely how mathematics is supposed to be formally encoded in the set theory. So a definition of a group would be an expression of this sort, which is probably about 2 pages long. And so computer scientists obviously needed to actually work with formalizations. And obviously, it's impossible to work with this type of formalization. So they invented something called type theory. And what is now coming to... So I have 20 minutes to speak, right? And then... So what is now... so type system is a totally different... belongs to a totally different class of formal languages where... So in logic, elementary pieces are sentences. In type theory, elementary pieces are sentences. In type theory, elementary pieces are called sequence. And they're typically written as follows: x1, t1, x2, t2, xn, tn, r. Now I'm underlying letters which denote expressions, as opposed to letters x1, x2, and so on, which denote single variables. So this this type of this thing is read as follows: so we're assuming that x1 is a variable of type t1, where t1 is some kind of expression. x2 is a variable of type t2, where t2 is a type some kind of expression, and so on. And under these assumptions, this expression r of x1 and xn will have type capital R of x1 and so on xn. Now, one need to consider some sort of examples, but the point. So now, the way one works with those things is that there are rules which permit one to construct new syntactically legal sequence out of old ones. For example, so the first part of the sequence is called context, and it's traditionally denoted by capital Greek letters. And the part after the turnstile symbol is called the judgment. So in this context, this judgment holds. And the typical construction would be the construction of dependent product, for example. If I have gamma RR, actually, I mean, so suppose gamma consists of this, and then I have this, then I can form a new sequence for which context will be just gamma without this thing, and the assertion will be that in the context gamma, I can form a product over all x in T of the corresponding R of x's in R of x's. So that's one of the ways to construct a new sequence from an old one. Now, it turns out that logic, as well as some kind of set theory, can be expressed entirely inside this type of formalism, so that this combines together both the deduction rules of the logic and the axioms. And that it's very convenient and actually can be quite efficiently used by people who need to describe some concrete structures. There is a big part of it which don't have time to go into. There is the whole theory of how to do inductive types, inductive definitions, and general work with inductive arguments inside this kind of approach, which is very ingenious. And once one have this, one can build all the same things as a set theory, except better. So.
What sort of symbols are allowed inside these?
So typically, so in the simplest, the simplest type theory is called type lambda calculus. It was invented by Church many years ago, and I don't think he used this particular notation, but in his version, one would have some generating types, some symbols which are just like letters in the alphabet, I mean. And then one would have the construction of dependent product, which will not be very dependent in that case, of lambda. So it's a branch of lambda calculus in a sense. So there will be this lambda expression for, I'll explain what lambda is. So if I have gamma, so I have the same thing as here. To start with, actually, what did I write? Sorry. that would be the rule for the formation of a dependent product. And that would be the rule for the formation of a member of dependent product. So in that case, I can write gamma lambda x TR. And that will be a member of the product of x TR. Now, it's hard to understand without some semantics assigned to it. And here is where the second half of the title comes in. So people have been looking for good semantics for type series, especially for complex type series, for many, many years. And there have been some very ingenious construction, like Dana-Scott construction for non-type lambda calculus. But basically, for the kind of languages which actually emerged in the practice of computer science, I mean, these languages emerged as practical tools of describing programs. No one knew any reasonable semantics. So the semantics where types are interpreted as sets and members of types are interpreted as elements of the sets, it never worked very well. And so what we've discovered recently, about 2 years ago, is that the correct semantics for this kind of languages one obtains if one considers types as to be homotopy types as opposed to sets. And then a lot of rich syntax of this kind of series finds its reflection in the structure of the homotopy category in totally amazing ways. And the more we work on it, the more we understand that this is the way to approach things like foundation of mathematics, for example. And instead of going through the set theory and formalizing mathematics in this unseemly way, one should one should go through type theory, and then what one gets a formalization, a syntactic formalization of the world of homotopy types suddenly, and instead of just the world of sets. So things like groupoids, for example, have independent meaning. You don't have to build a groupoid out of sets in order for it to have a meaning. There are types which are by birth groupoids. So when one wants to speak about things like the collection of all finite sets, it makes little sense to think about it as a set, because as a set it actually depends on the choice of a model very strongly. Like you have a slightly bigger model, there will be more one-point sets. Slightly smaller model will be fewer one-point sets. If you think about or finite sets in general. If you think about finite sets as a groupoid, then it doesn't matter how many actual members are there. Up to an equivalence, this groupoid will always be the same. And this type of things is extremely naturally expressed in this type theoretical language. And that's what I'm trying to promote and work on. Thank you.